12,900 years ago, something in the North Atlantic snapped. In one human lifetime, Northern Europe's temperature plummeted 10 to 15 degrees Celsius. The Sahara turned to dust. Tropical rain belts migrated. Ice reclaimed land that had been thawing for 2,000 years. In our field, we call this anomaly the Younger Dryas. Ice cores and deep-sea sediment tell us the cause was the collapse of the Atlantic conveyor belt. Today, every instrument we have pointed at that same conveyor belt is screaming one word at us: slowing. So if it happened once in a window as short as a decade, what exactly are we looking at when the data shows it repeating? If these planetary mysteries intrigue you as much as they do our team, hit like and subscribe so we can track this story together in real time. Tell me your location and local time in the comments. Do you believe we are being given the full truth about what is happening to our oceans? Let us examine part 1, the conveyor belt that engineered Europe. I want you to visualize something for a moment. View the entire Atlantic Ocean as a single, continent-spanning machine, not just a body of water. It is a heat redistribution engine the size of a hemisphere, pumping warm water north and cold south, on a loop that takes 1,000 years to finish. We call it the Atlantic Meridional Overturning Circulation, or the AMOC for short. The thing nobody tells you is that Europe is not actually Europe. London sits at the same latitude as Hudson Bay. Reflect on that for a second. Hudson Bay, the realm of polar bears, where the soil stays frozen 8 months a year and January averages minus 20 degrees Celsius. London should be a frozen wasteland. Berlin and Paris should look exactly like that. There is only one reason those cities are not currently buried under permafrost. Why can Norway grow wheat while Greenland is frozen? Why is Western Europe 5 to 10 degrees warmer than everywhere else on its latitude? It is all because of one thing. That ocean engine, the AMOC. According to a growing mountain of peer-reviewed data, this global engine is failing. I need to repeat that because it is the kind of warning that often slides past people on the first listen. The mechanism that built modern Europe and allowed 12,000 years of continuous human civilization in the North Atlantic basin, the largest mover of heat in our entire climate system, is failing. Not in the distant future, but now, measurably, and faster than any of our planetary models ever predicted. How does this system function, and why is it dying? Stay with me, because once we analyze the mechanism, you cannot unsee it. The AMOC begins in the equatorial Atlantic, where intense tropical radiation turns the surface into the hottest, saltiest water in the basin. It is hot from relentless sun, and salty because evaporation outpaces rainfall. The water leaves as vapor, but the salt stays behind. That dense hot water is captured by trade winds and forced north. It travels up the American coast as the famous Gulf Stream. You have heard of the Gulf Stream your whole life. It is essentially the southern artery of the AMOC. It transports a staggering amount of thermal energy, roughly 1.25 petawatts at its peak. To put that number into perspective, that is roughly 100 times the total electricity generation of every power plant on the planet combined. Every single one. Every solar farm, every nuclear plant, and every wind turbine added together times 100. All of that energy is being silently shoved north along the coast by the Atlantic every single day. That massive thermal load does not stay in the ocean. As the Gulf Stream flows toward Europe, it releases heat into the atmosphere. Prevailing westerly winds then carry that warmth across the entire continent. That is what defines European winters. It is why the snow melts in February instead of June. It is the very reason agricultural civilizations were able to thrive in northern Europe to begin with. You cannot run a civilization at the latitude of Hudson Bay without a permanent transfer of heat into your atmosphere. The AMOC is the only system doing that. Here is the critical part that is difficult to visualize. This is exactly where the engine is breaking down. By the time the water reaches the seas around Greenland and Norway, it has cooled significantly, It has surrendered its tropical warmth to Europe. It has exhausted its heat. Now comes the trick that makes the entire global conveyor work. That cold water, now heatless but still salty, becomes the densest seawater on our planet. Cold, salty, and incredibly heavy. Cold, salty, dense water sinks with massive force. It plunges down in columns several kilometers tall. We call this North Atlantic Deepwater Formation. It is the pump, the mechanical heart of the entire global circulation. If that sinking fails, the conveyor stops. Water no longer moves south at depth, and surface water is not pulled north. The entire loop breaks. Once that water plunges 4 kilometers down, it begins a slow crawl southward through the Atlantic abyss. It crosses the equator at depth and continues until it merges with the great Antarctic circumpolar current. From there, the water spreads into the global abyss, eventually rising back to the surface in the Indian and Pacific Oceans before starting the long journey back to the Atlantic. One full circuit from the surface to the abyss takes roughly 1,000 years to complete. 1,000 years for one drop of water to finish the loop. That is the sheer scale of this planetary system. It has been running continuously for the entire span of human civilization. Every empire and city in the Atlantic has been built on top of this machine. We have always stayed warm without ever checking the heating system, but now that planetary system is finally breaking down. Back in 2018, Levka Caesar and her team at the Potsdam Institute published a landmark paper in Nature, which is easily our field's most prestigious journal. Their approach was actually brilliant. We have only had direct sensors on the Atlantic conveyor since 2004. That is too little data to distinguish a trend from noise. So, Caesar looked for a signature. The logic was sound. If the current slows, the heat it carries toward the pole simply stops arriving. That means a specific area southeast of Greenland should be cooling, even as the rest of our planet continues to bake. They scanned over a century of sea surface temperature data and found exactly what they were looking for. A cold anomaly right where the physics predicted, bordered by hot water along the Gulf Stream. They used that data to trace the current back to 1870. The findings were chilling. The current has weakened by 15% since the 1950s. It is now at its lowest point in at least 1,000 years. Another study that year, led by David Thornalley, looked at something even more permanent. They pulled sediment cores from the deep Atlantic floor, reading the mud layer by layer like a geological archive. 1,600 years of planetary history were locked in those silt grains and microscopic fossils. This data was even more alarming. Thornalley's sediment record shows the current is weaker now than it has been in 16 centuries. 1,600 years. Roman emperors were still in power the last time the Atlantic water moved this slowly. The fall of the Western Roman Empire was happening in real time, and we are now, according to our sediment records, in a weaker state than ever since. That is the massive system we are dealing with. It is the engine driving our harvests and storm seasons. It has been running silently for as long as humans have recorded history. Now, across 5 research teams and 3 different methods, the data confirms it. The engine is failing. So now we have to face the most obvious question, the one that is likely the most terrifying of all. If this current built our modern world, but is now at its weakest point since antiquity, what happens to us next? Because the answer is hidden in a patch of ocean doing something no other patch on this planet is doing. It is getting colder. Part 2. The Cold Blob. I want you and I to look at a satellite map together. It is a global temperature anomaly reading, the kind we monitor daily. Red shows warming, blue shows cooling. Looking at the data from 1979 to today, the pattern is undeniable. Nearly the entire planet is red. The Pacific, the Indian Ocean, and the Mediterranean are all heating up. From the tropics to the Arctic, the map is stained blood red. Every major basin is absorbing heat. The rate of warming is startling when you see it from orbit. Every ocean is reacting. except for one. There is a single patch of water south of Greenland and Iceland that is defying the physics of the rest of the globe. On our temperature maps, that region shows up as a stubborn dark blue. While the world burns, this water is cooling. We have watched this cold blob on our satellites for 40 years, and it is not going away. If anything, the cooling is accelerating. For 20 years, we have tested every theory to explain why this one spot is different. We checked the clouds, the wind patterns, and the deep ocean mixing. One by one, every alternative theory was proven wrong. Only one explanation fits the location, the timing, and the physics of heat transport. The Atlantic conveyor is slowing down. Warm water is not reaching the north, so the surface there is failing to heat up like the rest of the world. This is the part that should truly haunt you. The signature of a dying current is not just a cold spot. It is that cold patch south of Greenland, coupled with intense, abnormal heat along the Gulf Stream. When the current stalls, the heat meant for Europe gets trapped. It piles up against the American coast, warming the water there at an extreme rate. It creates a perfect thermal fingerprint, cold in the north, hot in the west. It is a climate Rorschach test where, if you squint, you can see the ghost of an ocean current that is quite simply no longer doing its job. We have seen this signature in the satellite records for 50 years, and lately that image has only become sharper. Let's pause here, because this is the moment where the data starts to feel like a warning whispered directly into our ears. This is not some abstract model projection or a computer simulation. These are actual observations from our orbital platforms, recorded every single day for half a century. The photographs show a pattern that no other mechanism could create. The cold blob is a physical reality. It has been there for decades. It is the undeniable evidence of a failing planetary conveyor belt. The ocean is showing us a clue in a place where no clue should exist. It is a footprint in the snow that only one creature could have made. That cold anomaly isn't the only signature. Once we calibrated our sensors, the data began screaming from every quadrant. We've tracked the Gulf Stream drifting north and heating up over several decades of orbital observation. It is the expected result when the planetary heat sink fails to pull warm water toward Europe. The thermal boundary between these currents is migrating, dragging subtropical microorganisms into regions they've never belonged. These microscopic shelled organisms are appearing in Labrador Sea sediments, a clear anomaly in our fossil record. The intertropical convergence zone is the equatorial rain belt that dictates life or death for the Sahel. It's migrating south, confirming our models that show the planet's heat transport system is failing at the equator. This next variable affects us all directly. You and I need to look at rising sea levels along the coast. Our tide sensors show local sea levels rising 3 to 4 times faster than the rest of the planet. That's no minor deviation, it's massive. From our perspective, we analyse this using a 3-component model. Part of it is thermal expansion. Warm water simply occupies more space, a physical constant we see globally. Another factor is land subsidence, where the planetary crust itself sinks due to local geology and fluid extraction. That's localised but well documented. The final component involves ocean dynamics triggered by a faltering circulation engine. As this current slows, water accumulates along the western Atlantic. It has nowhere to go but up onto the land. It floods the coast, pours into streets, and breaches every seawall we've built to stop it. If you've watched king tides rise every season, you've personally witnessed this planetary system losing its momentum. When we redraw flood maps every 5 years, we're documenting a global failure in the form of local catastrophe. This isn't some distant projection. It's a live signal captured by every sensor from Maine down to Florida. We've analysed the extreme European winters of 2009 and the brutal cold anomaly we detected in 2017. These events correlate with the cold anomaly and a destabilised jet stream caused by a failing ocean engine. We can't attribute one blizzard to a single cause, but the atmospheric data shows a very clear trend. The total dataset reveals that Northern Europe is deviating from our standard models of a warming world. It matches the regional physics exactly. Our friends in the United Kingdom are already inhabiting a fundamentally shifted climate. Their weather is becoming erratic, showing cold anomalies that contradict the general thermal trend of the planet. Let's zoom out and look at the telemetry together. We see a massive thermal drop where it shouldn't exist. Plankton are migrating, rain belts are shifting, sea levels are surging. These are all global symptoms of one cause. Every data point we've collected points to the same culprit: the slow collapse of the Atlantic circulation. The evidence is so perfectly aligned it feels like a cosmic mystery solved by our own satellites. This signature is visible from orbit, deep in the sediment, and within our most advanced atmospheric sensors. The debate over whether this system is failing is over. Our instruments confirmed that reality years ago. Now we're calculating the velocity of this decline and watching for a catastrophic, non-linear tipping point. If this cold signature is the proof, then the planet has been signaling for 50 years of observation. We're finally deciphering the signal. But what is happening down in the deep abyss where we cannot see? What about the deep current our satellites can't image? That's where the primary engine of the planet resides. Only one sensor array has been tracking the deep flow for over 20 years. Let's look at part 3. The rapid array at 26.5 degrees north provides our first ground truth. Remember that coordinate. That invisible line across the ocean is where we decided to install a permanent planetary monitoring system. We've wired an entire latitude with sensors to measure the raw mechanical power of the Atlantic current. We measure the flow in spheredrops. One spheredrop equals 1 million cubic meters of water moving every second. When we report 17 spheredrops, it means 17 million cubic meters are surging past our sensors every second. That's like the entire Mississippi River being pumped north 1,000 times over, every single second. This engine moves more water in 1 second than all Earth's rivers combined move in a minute. That is the immense scale of this system. We began our direct measurements back in 2004. We call the array Rapid Mocha WBTS. The name reflects a massive multi-agency collaboration. RAPID is the Oceanography Centre's mission. MOCA belongs to Science Foundation. WBTS is the time series. Together, these three programs run a sensory grid of moored instruments spanning the Atlantic at 26.5 degrees north, plus a cluster of pressure sensors on the dark sea floor, and a brilliant hack involving the transatlantic telephone cable in the Florida Strait. We use this to calculate the Gulf Stream's massive flow by picking up faint electromagnetic pulses as salty water cuts through the Earth's magnetic field. Combined, we get a live, constant feed of planetary circulation across that line, 24 hours a day, every single day of the year. 2 decades into the mission, our readout is clear. The long-term average transport across 26.5 degrees north is roughly 17 spheredrops. Year to year, the signal is chaotic. Seasonal noise is everywhere. In this vast system, a single year of data is just a flicker in the void. It swings from 12 to 22 spheredrops annually. But over 20 years of constant observation, a chilling pattern has finally crystallized. Specifically, between 2004 and 2012, the sensors recorded a heavy and undeniable weakening in the flow. About 3 spheredrops, or 15% of the total engine power, has vanished. That is a massive shift, even against the background noise of the planet. David Smead and his colleagues published their analysis in 2018, and for those of us watching the data, it was a grim warning. The data shows that after 2008, the average strength of this planetary current is significantly lower than it was before. The decline has not worsened lately, but it has not recovered either. The current is idling at a plateau, 15% below its previous state. Since we first began tracking it, scientists have debated how much weight we can actually give to just 20 years of telemetry. This circulation fluctuates over centuries. In the life of a planet, a 20-year window is almost too narrow to define a permanent shift. Experts like Susan Lozier argue that this record could indicate human-driven decay, or simply a natural phase that might one day stabilise itself. Looking at the numbers in a vacuum, we cannot tell which future we are facing. The data itself is currently silent on the cause. But stick with me, because we are looking at a convergence of evidence. The data from the rapid array is not our only planetary sensor. The fingerprint analysis from the 2018 CESAR study is another critical piece of this orbital puzzle. The deep sediment records from Thornalley in 2018 provide even more context. Every one of these methods has its technical limits. Individually, they are debatable. Together, they align perfectly with the laws of physics regarding freshwater dilution and the density-driven sinking we expect. With Greenland melting at this rate, I must mention another sensor grid called OSNAP, which monitors the subpolar North Atlantic. Deployed in 2014, it sits much further north, right in the primary zone where the cold water begins its descent. This array gives us a direct look at the engine's core. Despite being a newer record, it confirms the broader signal of a slowing system. We are seeing the slowdown in the subpolar gyre. Combining rapid at the mid-latitudes with OSNAP in the north creates a massive diagnostic net. Between Argo floats and satellite altimetry from orbit, this is the most sophisticated monitoring network ever directed at a single planetary feature. You and I can see every instrument is returning the same data. The great heat engine of our planet is losing its momentum. It is not a total failure yet, but the slowdown is persistent and measurable. Nowhere in our telemetry do we see a sign of recovery. The rapid array is the gold standard for measuring this flow. It is truly one of the most vital scientific instruments of our century. It does not grab headlines. It does not have a catchy, dramatic name that people recognise. It is just a network of yellow buoys and concrete anchors resting in the deep, along with that humming cable in the Florida Strait. It is backed by a dedicated team of researchers who process these numbers in journals that the general public will likely never see. What they have been reporting with quiet persistence is that the largest thermodynamic engine on Earth is indeed losing power. Now we have to ask the critical question: why? What is actually causing this massive planetary system to grind to a halt? The answer lies on a frozen mass north of the cold blob, where ice that stood firm for 100,000 years is sliding. It is pouring into the sea at a rate we have never witnessed before. Let us look at Greenland and the 1600-year low. Before we focus on Greenland, I want to examine a study that dragged this orbital mystery into the light of mainstream science. Science is usually a slow grind of debates, but occasionally a finding is so profound that the entire community must stop and listen. In 2018, two major papers were published in the journal Nature just months apart. Both pointed to the same dark conclusion. Studies by CESAR and Thornalley achieved something we have sought for 30 years. They finally mapped the history of the Atlantic conveyor. They reconstructed the timeline of this massive current using two completely separate scientific methods, and both results were an identical match. CESAR's team worked like forensic investigators at a planetary crime scene to find the truth behind the missing circulation. We lack direct readings before 2004, so they had to measure the ripple effects that this current left behind in the past. They simulated various flow strengths in climate models to see how they would affect the surface of the ocean across the entire globe. They identified a specific thermal fingerprint that moves in total lockstep with the strength of the planet's overturning circulation. That signature is the cold blob and the warm Gulf Stream pattern that you and I analysed earlier in this mission. We could go back to the actual planetary sea surface temperature records, which exists in usable form back to the 1870s, and translate that data into a long-term strength estimate. The 2018 Nature report made the conclusion clear. Since the mid-20th century, this massive planetary engine has weakened by 15%. Most of that decline happened after 1985, matching the acceleration of Greenland's melting ice and the rising heat. The absolute strength of the circulation, as inferred from our sensors, is now weaker than at any point in the recorded temperature history, not by a little, but by a lot. In 2021, the giants of our field published a massive follow-up in Nature Climate Change. They used deeper data and ran consistency checks against multiple planetary climate model ensembles. They confirmed the original result. This circulation is not just weak, it is at a 1600-year low. But our fingerprint sensors only go back as far as the sea surface temperature records allow, which is the late 1800s. To see further back, we must scan the geological hard drive of the planet. That is where Thornalley's team came in. Thornalley and his colleagues at University College London approached the problem from a different angle. They pulled up massive mud cores from the bottom of the Atlantic graveyard. You and I should look at paleooceanography. It is one of those fields that feels almost magical once you understand the science. The deep ocean floor is essentially a planetary graveyard for data. Every year, a rain of microscopic organisms and mineral sediment settles into layers on the sea floor, accumulating century after century. In some undisturbed spots, these layers preserve a readable record stretching back hundreds of thousands of years. We can pull up a sediment core, slice it like a layer cake, and read planetary history 1 millimeter at a time. 20 centuries on, one mud core. Thornalley's team scanned 2 specific sites in the deep Atlantic and used 2 matching proxies. First, they looked at sortable silt grain size in the Iceland Basin. These are mud particles that are highly sensitive to the speed of the current. Fast currents carry larger grains. When the flow slows, only the fine dust remains behind. By measuring these grain sizes, we can reconstruct the speed of ancient ocean currents through the centuries. These bottom currents are driven by the entire engine. Faster grains mean the system is powered up, while finer grains mean weakness. The second data point came from tiny organisms called foraminifera. These are microscopic, single-celled organisms that build delicate shells and live in specific parts of the ocean depending on temperature and depth. Their shells are preserved in the mud forever. By cataloguing them, we can map the planet's past. Using this, we can reconstruct the exact location of the boundary between the cold Labrador Current and the warm Gulf Stream at any moment in history. That thermal front moves north and south based on the overall strength of the Atlantic circulation. We have 2 independent paleooceanographic sensors, one based on bottom currents and one on thermal fronts. You and I should see if they both record the same strength. They did. Both independent sensors told the exact same story. The system was stable for 1600 years, just the normal breathing of a healthy planet. Then, around 1850, the conveyor slowed down. Today, both proxies show the strength is at a 1600-year low. This matched the temperature method perfectly. The convergence of data was not a coincidence. It was a corroboration. There was a vital detail to note about that 1850 inflection point. It marks the end of the Little Ice Age. That was a cold era that lasted from 1300 until the mid-19th century across the northern hemisphere. Melting ice caps at that time poured fresh water into the North Atlantic, exactly the kind of input that would weaken the entire system. The historical context fits, the timing fits, and the physics of the mechanism fits. But now, the melting is driven by human warming. We need to take a step back and look at the total system. We took a system that had no direct measurement and reconstructed its planetary behaviour over 1,000 years using 2 independent methodologies, and both datasets agreed. The Great Atlantic Engine is now in its weakest state in approximately 1600 years. This is not a future model or a potential scenario. This is the empirical, peer-reviewed answer to where our planet stands right now. This is where the data gets dark. Those 2018 papers crystallised our concern, but they were just the leading edge of the warning. Then came more data in 2024, using salinity proxies. Recent findings in Science Advances suggest that our climate models have been systematically underestimating how fast this planetary engine actually responds to warming. And running underneath it all is the research applying tipping point mathematics to the question of when the entire circulation system could fully collapse. 5 major papers, 5 different methodologies, all converging on the same direction. Now you and I must ask, when the data agrees on a collapse, do we listen? My colleagues and I are building on the data Caesar and Thornalley published back in 2018. We are past the point of asking if. Now, as our models mature, we are calculating how fast and how far. That velocity depends almost entirely on the volume of fresh water dumping into the North Atlantic. This brings us to a massive, frozen island the size of Mexico, the primary source of that surge. It sits just north of that cold anomaly, bleeding mass into the ocean at a rate that has accelerated since the dawn of the 21st century. Our satellite gravity readings suggest this system might be crossing its own irreversible tipping point right now. Greenland is hemorrhaging into the North Atlantic. It is an environment nearly impossible to imagine if you have never seen it. Picture an area over twice the size of Texas. 80% of it is buried under ice up to 3 kilometers deep. This is the second largest ice mass on the planet, holding enough water to raise global seas by 7.5 meters. This ice sheet has remained stable in this configuration for over 100,000 years. It endured the end of the last ice age. It even survived the Holocene thermal peak, when temperatures were arguably higher than our current baseline. For all of human history, it was a stable constant in our climate system. Now, our sensors show it melting faster than at any point in the entire satellite record. Our GRACE satellite data through 2024 confirms the loss. Roughly 280 gigatons of ice vanish every single year. 1 gigaton equals 1 billion metric tons. That is 270 gigatons of cold fresh water pouring off the Greenland surface and straight into the surrounding ocean currents. Since our GRACE satellites launched in 2002, Greenland has lost 5,300 gigatons of ice. That is enough to raise the global mean sea level by 1.5 centimeters from a single island in just 22 years. And the velocity is increasing. Losses in the early 2000s were nothing compared to the mid-2010s. By 2023, we recorded the third lowest net surface mass balance in our entire 40-year history of observation. Even if 2024 was slightly less extreme, the long-term trend remains unbroken. Here is the AMOC connection. This is where our atmospheric physics and oceanography snap together. The AMOC relies on cold North Atlantic water sinking near Greenland, Iceland, and the Labrador Sea. If that water does not sink, the entire global heat pump fails. That sinking process requires water to be cold and extremely dense. In seawater, density is controlled by 2 primary variables: temperature and salinity. Cold water is heavy, salty water is heavy. From an orbital perspective, both are vital for circulation. In the modern North Atlantic, both of those pillars are failing. The water is warming and diluting, making it far too light to sink. We are seeing freshwater injection from exactly where you would expect. Greenland ice melt is dumping 270 gigatons into the system every single year. Arctic sea ice is also vanishing, with its minimum extent down 40% since we began monitoring in the 70s. A warmer atmosphere holds more water, driving intense rain and river discharge from Siberia and Canada, which is now flooding the Arctic Ocean with even more fresh runoff. This runoff exits through the Fram Strait, dumping directly into the same patch of ocean where the AMOC is supposed to sink and drive the global conveyor belt. When we aggregate the data, the freshwater forcing on the North Atlantic is completely unprecedented in our satellite history. The water that needs to sink to power the AMOC simply cannot. Every year, a massive volume of buoyant fresh water is poured right on top of the sinking zone. Fresh water floats on salt water, forming a less dense lid that resists vertical mixing. This physical mechanism is not subtle or theoretical. It is a proven fact. This is the same process that triggered every abrupt climate shift in Earth's history, including the Younger Dryas. You and I will look at the Younger Dryas shortly. It is the most critical historical blueprint for understanding our current planetary crisis. For now, understand this one crucial fact. Greenland is the primary driver of this destabilization. Ice that stood firm for 100 millennia is now bleeding into the exact patch of ocean that our sensors show is reaching a critical tipping point. The weakening of the AMOC, seen in our sediment and mooring data, matches the Greenland melt rate perfectly. The physics are aligning exactly as our models predicted. These global ocean consequences are not abstract. We have already measured the freshening of the North Atlantic's upper layers. We are witnessing the slowdown of deep water formation in the Labrador Sea and Denmark Strait. The system is stalling. Our instruments are already detecting significant changes in the subpolar gyre. Every single observation we make from orbit is consistent with the predicted impact of Greenland's fresh water on the AMOC. These shifts are happening right now, in real time, and buried within this data is a feedback loop that is genuinely terrifying to consider. As the AMOC slows, the heat transport toward the pole should logically decrease. You might think that would help preserve the ice, since warm water drives melting. But the planetary geometry is far more complex than that. That trapped heat builds up along the east coast of the United States instead. It also snakes into Greenland's fjords through deep subsurface channels that do not care about AMOC strength. Meanwhile, the rest of the high latitudes are warming rapidly through a process we call Arctic amplification. This causes the Arctic to warm at 4 times the global average, driving surface melt across the entire ice sheet, regardless of how weak the AMOC becomes. The feedback loop is asymmetric. Greenland feeds the weakening. It is a one-way trap, and you and I are watching the system amplify its own collapse. The AMOC weakening doesn't stop the heat. This feedback loop just spins faster and faster, until a freshwater pulse finally shoves the planetary system past its threshold. Where exactly is that threshold? Honestly, we don't know. We have never actually observed the AMOC crossing a tipping point in real time. We lack a calibrated value for the force needed to flip the system. But the paleoclimate record tells us it has happened many times before. It has happened 20+ times in the last 100,000 years, in fact. We see them in the data as Heinrich events and Dansgaard-Oeschger oscillations. Every one of those events was fueled by a mix of glacial freshwater surges and atmospheric pressure. These triggered abrupt climate shifts across the northern hemisphere, swinging temperatures by 5 to 15 degrees in just a decade. Back then, Earth's ice volume was far greater than it is today. A small fraction of melt from those massive sheets was enough to flip the whole system. We don't have those ancient ice sheets today. We have Greenland. And Greenland is hemorrhaging 270 gigatons every year, with the pace only accelerating. Look at the math. If this current trajectory holds, Greenland could be shedding 500 gigatons of ice per year, or even more, by mid-century. By the year 2050, the cumulative loss could reach somewhere around 15 to 20,000 gigatons of ice. That freshwater volume starts to look significant even compared to the Heinrich events, but it's arriving over decades, not millennia. It is the physics chain, end to end. Human-caused warming drives up global temperatures. The Arctic heats 4 times faster than the average, causing Greenland's surface to melt with increasing aggression. 270 gigatons of fresh water flood the North Atlantic every year. The surface freshens, creating a lid that refuses to sink. Deep water formation slows down. The AMOC weakens. We can see the fingerprint in sea surface temperatures and deep sediment cores. The signal is in the rapid data, sea levels on the east coast, European jet stream shifts, and Sahel rainfall. These markers are all visible right now. And the engine of this collapse, the primary driver, is sitting just north of us, literally bleeding out into the ocean. The question we must ask is simple. How much further can this go before we finally cross the threshold? Back in 2023, 2 scientists in Copenhagen tackled that exact question, using the same mathematics that predicts everything from ecosystem collapse to major financial crashes. They ran the model and it spat out a specific year, a date with a narrow confidence interval that lands well within our lifetimes. Part 6. Ditlevson 2057 and the tipping point math. In July of 2023, a paper hit Nature Communications that rattled the scientific community to its core. The authors were Peter and Suzanne Ditlevson, a team working out of the University of Copenhagen. Peter is a glaciologist and physicist. Suzanne is a specialist in statistics. Together, they applied a tool called early warning signal analysis to the historical sea surface temperature records of the subpolar North Atlantic. They focused on the very same cold blob region to estimate exactly when the AMOC might fully collapse. The resulting date they calculated was 2057. The 95% confidence interval spans from 2025 at the low end to 2095 at the top. Let's look at what early warning signal analysis actually is. If you call it statistics, it sounds boring, but once you see it in action, it's a genuinely strange and powerful piece of science. Picture a marble sitting in a bowl. The bowl's shape represents the system's stable state, where gravity pulls the marble back to center whenever it gets nudged. Nudge the marble, and it rolls up the side before rolling back down. The speed of that recovery depends on how steep the bowl is. A steep bowl means fast recovery. A shallow bowl means slow recovery. Now imagine that bowl is slowly starting to flatten out. The walls aren't as steep anymore. As the bowl flattens, the marble's bounce back begins to slow down. The motion becomes more correlated because the marble lingers where it was nudged instead of snapping back. Variance grows because that same nudge pushes it further. Eventually, the bowl gets so flat that a single moderate nudge sends the marble flying out. That, right there, is a tipping point. Complex systems math proves that before the actual tipping point, we can detect the bowl flattening by observing the specific statistics of the system's planetary motion. Two indicators grow near a tipping point. First, autocorrelation, which measures how much each data point depends on the one before it. Second is variance, the measure of how wildly the system swings away from its average. If you see both quantities growing systematically over time in a complex real-world system, you're looking at the statistical fingerprint of a looming tipping point. Scientists call this phenomenon critical slowing down. We have observed this in various complex systems, from ecosystem collapses and volcanic eruptions to stock market crashes and even seizures in the human brain. The mathematics is sound, but interpreting that math in the real world, that is where the scientific controversy really begins. The Ditlevsons analysed the cold blob's annual sea surface temperatures from 1870 all the way to 2020. After applying early warning signal analysis, they found that both autocorrelation and variance were growing in a way that matches critical slowing down. Their conclusion was clear. The AMOC, as seen through the cold blob data, is nearing its tipping point. They then fit a stochastic model to the trend and projected it forward to calculate exactly when the system would finally lose stability. That is the point of transition. Their central estimate was 2057, with the 95% confidence interval spanning 2025 to 2095. 2057. That's barely 30 years away. Many of you watching this right now will still be alive in 2057. You might be middle-aged or retired then. Some of you will be raising children who haven't even been born yet. According to the best estimates in Nature Communications, that is the date. The year our planet's vital Atlantic heat engine finally shuts down. I need to be perfectly honest with you about what this data actually reveals. The controversy is significant, and we should keep our scientific skepticism fully engaged. These researchers did not definitively predict a total collapse by 2057. They generated a single statistical projection laden with uncertainty based on one narrow methodology and a specific proxy for the ocean's current strength. The study faces technical criticism. That cold blob temperature record, while extensive, is not a direct, clean observation of how the Atlantic engine is actually performing. It is merely a planetary fingerprint, influenced by complex atmospheric and oceanic variables. While those early warning signals work elsewhere, applying that mathematics to long-term climate data remains a subject of intense scientific debate. The data noise is high, burying the signal in decades of chaos. Plus, assuming we can just linearly project the past to find a tipping point is risky. That requires a level of modelling confidence that many top oceanographers at the National Oceanography Centre and NOAA have openly doubted in their peer reviews. This study is not the final word. It is just one data point in a vast planetary puzzle, but it matters. Even if we ignore the 2057 date, call the methods too bold, and push the timeline back to 2070 or even 2090, the reality that a top-tier, peer-reviewed analysis provides a 95% confidence interval is quite chilling to any observer. Having a lower bound starting in 2025, with a central estimate within our lifetimes, is a massive telemetry alert for the scientific community. For 30 years, we viewed a total circulation collapse as a distant, low-probability event for the 22nd century, or even further out. The 2021 IPCC report called a collapse unlikely before 2100, yet they explicitly noted low confidence because our current planetary models are limited. These researchers did not invent the fear, they simply quantified what many in the earth science community have been whispering behind closed doors for years. Take Stefan Rahmstorf, a veteran researcher who has spent 35 years monitoring the Atlantic's vital signs from his ground station. He has stated publicly that the odds of a full shutdown by the middle of this century are now over 50%. He warns that a total collapse would be the most violent planetary shift seen in 100,000 years. In 2021, Nicholas Bohr's published data suggesting our primary ocean current may have already lost stability and is nearing a fatal tipping point. Peter Cox has found evidence that the ocean responds much faster to warming than our models predicted. The issue is not just a single paper. The critical point is that a large group of senior, highly respected planetary scientists have collectively grown far more concerned about our collapsing timeline recently. You and I can see that this controversial 2023 study actually aligns perfectly with a broader, more terrifying shift in scientific consensus. Keep that date in mind as we continue, because the entire planetary physics of what comes next depends on it. We will look at historical analogues like the Younger Dryas, Stommel's bistability, and the latest emergent constraint data. The devastating effects on Europe, the American coast, and the Sahel all lead back to one terrifying planetary question. Is that estimate too aggressive, or is 2057 actually a realistic trajectory for the end of the world? Have our global models been underestimating how fast this planetary engine can fail? There is only one way for us to find the answer. To ground truth a statistical projection of a system we have never seen fail, we must scan the deep geological record for the last time it actually broke. We need to observe what the planet looked like after the last tipping point, and we have found an analogue. We possess an incredibly detailed record of a sudden climate flip in Earth's history. It occurred 12,900 years ago. It struck like a cosmic hammer and lasted 12 centuries. Part 7. 12,900 years ago, our world was emerging from the Ice Age. Massive continental ice sheets were in retreat, North America was losing its frozen shell, and Europe was finally starting to warm. Oceans rose as the glaciers melted. Life began colonizing vast territories that had been locked in ice for eons. The first humans were successfully migrating across the Americas, establishing their presence on a changing planet. The northern hemisphere had been warming for 2,000 years. The data shows the climate was steadily stabilizing toward modern and hospitable interglacial conditions. Conditions were rapidly improving for any early humans surviving in Europe. Then, in a sudden geological heartbeat, the entire planetary climate slammed back into a freeze. We call this event the Younger Dryas. It is named after a hardy tundra flower, the Dryas octopetala, whose pollen suddenly resurfaced in the geological record. This cold-loving flower essentially reclaimed the land. Not just the flower, but the entire tundra biome returned. Cold-adapted species suddenly dominated the landscape once again. Our ice core data suggests that in just 1 to 3 decades, the climate flipped from a warm recovery back into a full ice age. These planetary numbers are staggering, and I need you to hear them. Greenland ice core records show temperatures plunging by 10 to 15 degrees Celsius in mere decades. This is not a sensor error. A 10 to 15 degree cooling event, hitting in decades and maintaining its grip on the Northern Hemisphere for 1,200 years. Then, just as abruptly, the planetary system flipped back, and our modern warm era finally began. Since then, we have occupied the Holocene, this stable thermal pocket where agriculture thrived and cities rose. It is the only biosphere we have ever known. This climate alone allowed our civilization to exist. But looking at the Younger Dryas, we see a planetary system that flipped twice in just 1,400 years. Our data from Atlantic sediment and North American lake records points toward one primary cause for both of these massive systemic shifts. A colossal release of meltwater from Lake Agassiz flooded the North Atlantic, effectively shutting down the entire AMOC current. When the freshwater slowed and salinity recovered, the system finally restarted. I want us to study Lake Agassiz together. To a geologist, it is a footnote, but it shaped human history more than almost any other body of water. It was a proglacial lake, essentially a massive reservoir of meltwater trapped against the retreating southern wall of the Laurentide ice sheet. This continental glacier was a monster, burying most of Canada and the northern United States beneath miles of ice during the last ice age. As the Laurentide receded, meltwater pooled in the massive basin between the ice and the higher ground to the south. At its peak, Agassiz covered 440,000 square kilometres. That is larger than all 5 of our modern Great Lakes combined. It held an astronomical volume of cold, fresh water, sitting behind a natural dam and waiting for the right moment to fail. The tipping point arrived. While we debate the specifics, the ice likely retreated just far enough to hit a critical drainage threshold. Suddenly, Lake Agassiz suffered a catastrophic drainage event through the St. Lawrence or Mackenzie systems, dumping its entire frozen volume into the North Atlantic or the Arctic Ocean. Both paths delivered a massive payload, 9,500 cubic kilometres of fresh water. That is a staggering amount of fluid to move at once. This flood hit the North Atlantic over just a few decades. It did exactly what we see Greenland doing now, but in terrifying fast forward. This fresh water capped the North Atlantic, blocking the formation of deep water and effectively shutting down the AMOC heat pump that drives our climate. This is what should haunt us. Within mere decades, the heat transport system that keeps Europe habitable simply collapsed under the weight of that water. It did not just slow down, it failed. Sea ice surged south, the drift vanished, and air temperatures across Europe plummeted. The Sahara, once a lush landscape, dried up. The monsoons across Africa and South Asia weakened and shifted toward the southern hemisphere. Rainfall belts feeding the Nile shifted entirely. Once the AMOC shut down, the planetary climate stabilized into a new and brutal cold regime. This state lasted for 1,200 years. That is the entire timeline from the founding of Rome to the final fall of the Western Empire. 1,200 years is longer than the time since the Battle of Hastings. It is longer than any human empire has ever managed to survive. That was the duration of the Younger Dryas. 1,200 years of glacial conditions and a Europe frozen in time. For 1,200 years, the Sahara stayed dry, monsoons failed, and the climate remained in a harsh state, completely unlike the one our civilization was built on. Then, it abruptly ended. The AMOC restarted, the climate flicked back, and the warm Holocene era we live in finally began. The Younger Dryas is not some isolated anomaly. It is simply the most recent and well-documented example of an AMOC shutdown. If we look further back into the ice cores, we see a sequence of identical catastrophes called Heinrich events. They are named after Hartmut Heinrich, the scientist who discovered these traces in the deep sediment of the Atlantic floor. During these events, massive armadas of icebergs broke off the ice sheet, flooding the North Atlantic with fresh water and sediment right where the ocean current sinks down. We have identified 6 major Heinrich events in the record, labelled H6 through H1, stretching across the last glacial period. Each one triggered a sudden climate transition, causing abrupt cooling in the north and disrupting vital rainfall patterns across the tropics. Alongside these were the Dansgaard-Oskar oscillations, roughly 25 rapid climate shifts that occurred over the last 100,000 years. Each involved a burst of warming over a few decades, followed by slow cooling and then a sudden drop back into the cold. Greenland ice cores show these temperature swings of 5 to 15 degrees Celsius happening in as little as a single decade. While we still debate the specific triggers, the scientific consensus is that these events represent the AMOC flipping between different stable modes. The paleoclimate record presents an uncomfortable reality. This system does not change gradually. It is not a smooth ride. It is a system with multiple stable states, and it has flipped between them about 20 times in the last 100,000 years. Each flip shifted northern temperatures by 5 to 15 degrees Celsius in just 1 to 3 decades. That is a massive global shock. Once it flips, the planet stays in that state for over a millennium. We have to consider what we are currently doing to this fragile system. We are performing the one action known to trigger a flip, dumping fresh water into the North Atlantic at an accelerating pace. The question of a modern climate flip is not some abstract hypothetical. It is about how close we are to the breaking point. The comparison to the Younger Dryas is particularly haunting. The Agassiz pulse was roughly 9,500 cubic kilometers, delivered over several decades. Since 2002, the Greenland ice sheet has already dumped about 5,300 gigatons of fresh water into the sea. That is 5,300 cubic kilometers. We are roughly 20 years away from dumping a Lake Agassiz volume into the exact same region of ocean. The only difference is we are doing it through a steady leak rather than a single, catastrophic burst. Whether that difference saves us, or if a slow pulse is just as deadly as a sudden one, remains the most critical debate in our field. The optimistic hypothesis is that slow delivery allows the ocean to reach equilibrium. Circulation is suppressed, but it is not a total catastrophe. The pessimistic view is that cumulative effects matter most. This slow delivery might just be delaying a non-linear collapse like the Younger Dryas. We still do not know which view is correct. Decades of incoming data from tide gauges, mooring sensors, and sediment cores will eventually tell us. The Younger Dryas is our benchmark for the worst case. That AMOC collapse is etched into ice cores and lake mud, with enough scientific detail to leave no ambiguity about what the climate did. It sits in the geological record like a dark mirror. This is not a theory. This future is documented in the rock. If a freshwater pulse from one melting ice sheet was enough to trigger it once, then a similar pulse from a different glacier could trigger it all over again. If the system can flip, and the paleoclimate record proves that it can, the only remaining question is the threshold. What is the tipping point? How much freshwater or cold blob expansion pushes the system from a recoverable slowdown into an irreversible shutdown? To understand that, you and I must analyse 1961 mathematics from a brilliant MIT oceanographer named Henry Stommel. His paper sat ignored for decades. This is part 8. Stommel's bistability and the door that locks behind you. Henry Stommel was an oceanographer who published an elegant paper in the journal Tellus in 1961. He titled it Thermal Convection with Two Stable Regimes of Flow. We call it the Stommel two-box model. It was a simple thought experiment. Imagine two ocean basins connected by a shallow channel. One basin at the tropics and one at the poles. Heat and freshwater exchange push these basins toward equilibrium. Meanwhile, water flows through the channel, driven entirely by the massive density differences between the poles and the tropics. Stommel solved the equations for these equilibrium states. He discovered something very peculiar. The system has two stable paths. One where polar water sinks, driving a strong current that carries warm water toward the northern latitudes. In the other, polar water is fresher and lighter. It does not sink. The circulation collapses into a weak flow. In Stommel's model, the system is bistable, like a light switch with two settings, strong or weak. The transition between states is not gradual, it is abrupt. Cross the threshold and the system flips. His paper was ignored for 30 years, but by the 1990s, after studying the Heinrich events, our community finally recognized the implications of Stommel's bistability. This was no mathematical curiosity. It was the mechanism behind every abrupt climate transition we find in the paleoclimate record. The AMOC flips because the Atlantic's density structure supports two stable regimes. Crossing a freshwater threshold is enough to trigger the switch. There is one more feature of the Stommel model to discuss. As a scientist, it is the most uncomfortable one. These two stable states are not symmetric in their relationship to freshwater forcing. To switch from strong overturning to weak, you must push past a high threshold. But to switch back, you cannot just return the salt levels to where they were. You must drop them much lower. We call this hysteresis. The system has memory. The way back is not the way in. If the Atlantic current flips, simply stopping the Greenland melt is not enough to bring it back. We would have to cool the North Atlantic and refreeze massive volumes of ice just to overcome the system's preference for its new state. On human policy timescales, that is impossible. When the door closes, it locks. That 2008 paper in the PNAS identified the AMOC as a tipping element specifically because of this behaviour. Our framework distinguishes between climate features that respond smoothly and those that exhibit threshold behaviour with multiple stable states. The AMOC was placed in the highest priority category alongside the Greenland ice sheet and the Amazon rainforest. These are our primary tipping elements. Once you cross the threshold in any of these systems, you cannot easily go back. The forcing required to break them is much smaller than the forcing required to fix them. The real world's bistability is still debated. Recent CMIP6 simulations suggest that under realistic forcing, the Atlantic current might weaken slowly rather than collapsing. The system would weaken step by step rather than crushing abruptly. Others argue that early warning signals of this bistable behaviour are already visible in our observational data. This disagreement is the frontier of our research. It is unlikely to be resolved anytime soon. But when the cost of being wrong is this high, the precautionary principle starts to dominate our global policy conversations. If there is even a moderate chance of a Stommel-style collapse, we face 1,200 years of ice over northern Europe. The calculus is no longer about raw certainty. It is about decision-making under uncertainty in a system with unimaginable consequences. So let us bring our focus back to the leading edge of where science stands today. In 2026, a new paper changed everything. That paper suggests that if these findings hold, our standard projections and every government adaptation plan on Earth are fundamentally wrong. We might be miscalculating how fast Earth's heat engine is shifting. Portman 2026 proves our models are lagging behind. Christine Portman and her team recently published a paper in Science Advances regarding the planetary circulation's sensitivity to our warming footprint. To understand these findings, you and I need to look at how we actually simulate a planet's climate in the lab. Once you see the math, the danger becomes clear. Our standard tools, the general circulation models, are what govern global climate reports. They simulate the atmosphere, the oceans, the ice, and the very surface of the planet. They also calculate chemical cycles on a planetary grid, with resolution points spaced from 10 to 100 kilometers across the entire globe. The software solves complex equations for fluid motion, heat transfer, and thermodynamics across every single cell in that digital world. We push these simulations forward in time steps as short as minutes. They are massive engineering triumphs, yet they are far from perfect. Many vital physical processes happen at scales far smaller than our sensors can track, so we have to use estimates instead. We use simplified math to guess at things like cloud formation, ocean mixing, and the way sea ice ridges together under pressure. Every model has dials we can turn, and different research teams across the world make different calls on those settings. Because of this, the dozens of models in the Coupled Model Intercomparison project rarely show us the exact same future. They produce a spectrum of possible outcomes. This spread is exactly where the uncertainty in our official global projections comes from. While they agree on surface temperatures, they differ wildly when calculating the strength of the Atlantic's massive circulation engine. Estimates for the slowdown by 2100 vary from 20% to 40% under our current emission trajectories. That gap is enormous. It means the difference between a manageable shift and a total catastrophe for Europe and the tropics. So, can we do better? Can we use actual satellite data to figure out which of these simulations is telling the truth? That is the role of an emergent constraint. We find something we can see today that predicts how the system will react later. If we find that link, we can use our current observations to discard the models that are clearly drifting off course. This technique has been used to track everything from cloud patterns to the melting edge of the Arctic sea ice. Portman and her team applied this orbital-level logic directly to the Atlantic circulation. They found a link between current sea surface temperatures and how much the models predicted the entire system would eventually fail. Models showing a severe cold blob today, with freezing water south of Greenland and heat along the Gulf Stream, predicted a much larger collapse by 2100. This correlation was finally strong enough to give us a reliable constraint. Then they compared it to what our instruments actually see in the North Atlantic right now. They used those real-world observations to determine which of the models, from the 20 to 40% range, actually match our current reality. The data revealed something terrifying. The most accurate models weren't the moderate ones, they were the ones showing the most extreme damage. If this pattern holds, the Portman study implies the Atlantic circulation will weaken by 50% before this century is even out. The confidence range sits between 42 and 58%. That is 50% stronger than standard projections and higher than almost any individual model result. The terrifying implication is that the very models we use to plan for the future are fundamentally flawed at their core. This affects every safety plan for Europe, the American coast, and South Asia. Our survival blueprints are based on the wrong numbers. We are underestimating the speed of this planetary shift by nearly double. The system is moving faster than our computers can imagine. And if we are wrong about the circulation, every prediction about floods, droughts, and sea level rise is also dangerously low. I must be objective. This is one team using one specific lens on the data. We need to verify these findings. These constraints are powerful tools, but they are not infallible. The rest of the scientific community is still processing this shock. The honest take is that Portman represents a new methodology, suggesting the ocean is failing much faster than the official consensus ever dared to state. It suggests our simulations don't truly understand how sensitive the North Atlantic is to the influx of melting fresh water. The full implications of this, including whether the next generation of simulations will finally learn these lessons, are still being worked out in the scientific literature. But the trajectory is obvious. We are not looking at a slow, gentle transition for our planet's life support system. It is fast and aggressive. The 2057 collapse estimate is looking much more realistic. In the light of this new data, previous warnings like the 600-year low in 2018 are no longer outliers. They are the new baseline. The cold blob is no longer just a curious feature on our maps. It is an active alarm for a system breaking apart. Every piece of evidence we collect points to the same conclusion. The circulation is weaker than our models showed, and it is failing much faster. We are approaching the threshold where the very chemistry of the salt water could trigger a permanent, irreversible shift in the global climate. You and I need to look at what a 50% slowdown actually means for the biosphere, because this is not theoretical. It is not a distant theory. It is not science fiction. This is our primary data projection for 2100. We are documenting a total restructuring of the Atlantic climate map. Here is how a 50% slowdown looks. Join me in this planetary simulation. It is 2100 and the Atlantic circulation has dropped by half. This matches the Postman data models. We are assuming carbon emissions stayed on a moderate, middle-of-the-road path. Meanwhile, the rest of the planet continues its thermal climb, tracking perfectly with our global mean surface temperature projections. But what does our biosphere actually look like? Looking down at northwestern Europe, the readings are deeply strange. Most of the planet is running a fever. The tropics are dangerously hot. The Mediterranean is becoming a parched wasteland. Heat is rising across southern Europe, but over the United Kingdom and Germany, that expected warming has not happened. Winter signatures are particularly interesting. They remain locked at current levels, or in some scenarios, they have actually cooled. The reason is that the failing ocean circulation can no longer transport enough heat northward to maintain those historic temperatures. The North Atlantic cold blob is expanding. Jet stream behaviour has become erratic, showing frequent and dangerous meridional swings. This funnels Arctic air directly over Europe. We are documenting what researchers call regional cooling in an otherwise warming world. It is not a sudden ice age, but a significant 3 degrees Celsius offset compared to the global average temperature. This leaves northwestern Europe trapped in 2025, at least thermally, but with far more volatile and unpredictable weather. Brutal winters like we saw in 2017 are now common. We also see frequent cycles of persistently cool, wet summers. European crop yields are fluctuating wildly beyond the system's design. Heating demand stays high, even as the planet warms elsewhere. Coastal storms gain massive energy. The thermal contrast between the poles and tropics is driving intense, high-pressure atmospheric gradients. This triggers more intense cyclones across Western Europe. But let us shift our gaze to the United States. The data is different. Sea levels along the east coast are accelerating. Cities like New York are seeing rises 4 times higher than the global average. A 50% slowdown by 2100 pushes that regional offset 30 centimetres higher than the rest of the ocean. Keep in mind that 30 centimetres is added to the global sea level rise of roughly 1 metre. You are looking at an east coast where the effective sea level has surged by 1.5 metres. This impacts every major hub, from Boston and New York down to Charleston, Jacksonville and Miami. The threats of coastal flooding and aquifer contamination are no longer abstract. They are becoming hard operational realities. These are active problems. Engineers are already redrawing maps and planning massive seawalls to hold back the tides. The rapid sea level rise from this weakening circulation turns a manageable challenge into an existential crisis. Down in the tropics, the consequences are even more profound, yet they are rarely mentioned in mainstream coverage. Our ocean acts as a massive planetary heat pump. When it weakens, that vital northward thermal transport simply fails. The Atlantic rain belt, which determines the water supply for the African Sahel, is beginning to shift its position. Specifically, it is drifting south, away from the Sahel. Millions from Senegal to Sudan depend on this rain to survive. A shift of just a few hundred kilometres is enough to destroy Sahelian agriculture and regional food security. We see this in the paleoclimate record from the Younger Dryas, when a similar shift scorched the entire region. Look at the African droughts of the 1960s. Natural variability triggered a famine that devastated the entire continent. Our latest simulations show that a 50% weakening causes a shift far beyond the natural variability of the past. The implications for 400 million people in the Sahel and the food security of West Africa are staggering. North Africa and Southern Europe will become primary destinations for climate refugees. The scale of this movement is immense. The South Asian monsoon, which feeds 2 billion people, is fundamentally linked to these North Atlantic circulation patterns. Atmospheric teleconnections suggest that a weakening ocean circulation will likely reduce the intensity of these vital monsoons. Quantifying the exact impact on South Asian agriculture is difficult, but our data points in a negative direction. In the global ocean, the damage goes deep. North Atlantic fisheries rely on nutrient-rich upwelling that is now failing. We are seeing massive species migrations and population collapses. Cod stocks, already struggling, face a new, deadly pressure. Warm water species are migrating north, while cold-adapted populations lose their habitat as the ocean's thermal map shifts. Atlantic salmon runs are collapsing. The fundamental reorganization of the marine food web is now accelerating beyond our control. In the Amazon, these altered rain patterns are pushing the rainforest toward a catastrophic and irreversible dieback. We are witnessing a planetary tipping point. These shifts are pushing the entire biosphere toward an irreversible state. Think of the Amazon as its own planetary feedback loop. We see it coupled with the AMOC, where deep ocean cooling directly shifts tropical sea surface temperatures. This disrupts rainfall patterns, stripping the rainforest of its natural defense against deforestation. When the AMOC falters, the pressure on the Amazon reaches a critical breaking point. It pushes the ecosystem toward a catastrophic threshold within our lifetimes. Now, if we pivot to the Antarctic, the data looks truly anomalous. Our simulation models indicate that failing northward heat transport traps thermal energy in the Southern Ocean, essentially boiling the system from below. The destabilization starting in Greenland eventually propagates south, triggering a runaway melt across the entire Antarctic ice shelf. This feedback loop drives global sea level surges and fundamentally rewires ocean currents. The entire planetary system is interconnected. One system failure triggers the next. A 50% slowdown by the year 2100 would effectively erase our current climate map of the entire Atlantic basin. This isn't a sudden descent into a new ice age. It's not some cinematic catastrophe where Manhattan freezes in a single night. It's a more insidious, pervasive shift. We're witnessing a slow, permanent reorganization of global precipitation, storm trajectories, and where catastrophic coastal flooding happens. This includes where our global agricultural belts can sustain themselves. It's a reorganization our cities and farms were simply never engineered to survive. Global fisheries and insurance markets are completely unprepared. This isn't some outlier scenario, it's actually our central scientific expectation for the future. You and I are likely to witness this ourselves. This is what the data predicts will occur within the current human lifespan. If that's the baseline, then a total planetary collapse, a full stomal event, becomes the terrifying tail risk we must analyse. The real question is how we quantify that risk and whether it's been scrubbed from public discourse. That's where the conspiracy and counter-narrative theories gain traction. Many of these claims are purely unscientific. However, others expose massive gaps in the actual conversation we should be having. Let's examine the evidence together. Part 11. Conspiracies, systematic cover-ups, and the cold, honest data. Whenever a major planetary tipping point enters the public discussion with such catastrophic implications, theories of conspiracy and cover-up are sure to follow right behind. That is the reality of processing high-stakes planetary data in our modern information landscape. I want to walk through the most common conspiracy framings, examine the logic behind them, and then show you what our satellite data and global sensors actually tell us. Theory number 1. Governments and the media are suppressing AMOC data to protect the interests of the fossil fuel industry. The strongest argument for this is the massive disconnect between our laboratory findings and actual political action. The scientific community identifies the AMOC as a threat, yet fossil fuel expansion continues. On the surface, this looks like a direct contradiction. However, the rebuttal is purely structural. Our findings are published openly in the most prestigious scientific journals on the planet. I'm talking about high-impact journals like Nature and Science. Furthermore, every major news outlet from the BBC to the Washington Post has reported on this. The latest international reports explicitly categorize the AMOC as a planetary tipping element. There's zero evidence of data suppression. The disconnect between data and policy is a political failure, not a secret censorship campaign. Our scientific findings are entirely in the open. The real issue is total political inaction. The second claim suggests that geoengineering, atmospheric modification, and projects like HARP are what's actually weakening the global current system. This argument follows the same logic as most other theories involving large-scale weather modification and atmospheric control. But from a physics standpoint, the energy budget argument debunking this is overwhelming and scientifically conclusive. The freshwater flux from Greenland's ice melt at 270 gigatons per year represents a truly colossal energy injection of roughly 10 to the 21st power joules. That's simply the latent heat from the melting ice. Comparatively, the energy output of every proposed geoengineering intervention worldwide is only 10 to the 15th joules per year. The geoengineering signal is 6 or 7 orders of magnitude too weak to even influence a system this massive. Even if our current atmospheric modification projects were impossibly powerful, the fundamental energy budget of the planet simply does not support the theory at all. The melt rate in Greenland alone accounts for the forcing we see in the North Atlantic. No other variables are required. The third claim asserts that an AMOC collapse is imminent within 10 years, and that authorities are suppressing this to avoid global panic. This theory cites the 2025 lower bound found in the recent Ditlevson statistical confidence intervals. The rebuttal is clear. That 2025 date represents the absolute extreme edge of a 95% confidence interval in one specific analysis. Many in the oceanographic community question that specific methodology. Our central estimate actually points to 2057, not 2025. Additionally, our global satellite and sensor arrays would detect a massive acceleration of weakening if a collapse were actually expected in the next few years. Our current data shows a steady weakening at trend rates, not the sharp, non-linear acceleration that usually signals an immediate planetary collapse. Scientifically, an imminent collapse is possible, though unlikely. Rest assured, our global monitoring systems would catch the signals well before it occurred. We are watching closely, but panic isn't justified yet. The fourth claim suggests this weakening is just a natural cycle, like solar fluctuations or ocean oscillation cycles. This argument denies that human warming is the cause, noting that multi-decadal ocean cycles naturally produce significant shifts in temperature and flow. These cycles affect North Atlantic surface temperatures. Frankly, our post-2004 data is too brief to definitively separate natural variability from the warming trend. However, our paleoclimate data says otherwise. Looking at the 2018 Thorn Alley cores, this post-1850 weakening is totally unprecedented in our 1600-year record. It completely dwarfs any natural cycle we find in the proxy data. Caesar's 2018 work directly tackles the man-made versus natural debate. Our models show that this cold blob signature isn't natural. It is a perfect match for the man-made fingerprint we predicted years ago. Natural cycles just cannot account for this magnitude. Sure, internal noise exists, but it does not create a 1600-year record low. Then there is the counter-argument that everything is fine and we are just inflating the danger to secure more research grants. To be fair, my colleagues and I have occasionally published findings that turned out to be a bit premature in the past. Take those early 2000s headlines. The Bryden paper was later corrected once we gathered more substantial long-term data for the field. The rebuttal is simple. The 2005 result was just a snapshot. Once continuous monitoring via the rapid array began in 2004, we finally refined our models. But the new data did not erase the trend. It confirmed it. Now, our paleoclimate fingerprints and observational constraints are all converging. We are seeing the same direction across the board. This consensus is not based on one sensational paper, but on multiple independent streams of evidence. Honestly, the claim that we are exaggerating falls apart when you and I look at the mountain of evidence we have just reviewed. From my seat in the lab, looking at the literature every day, I can tell you this is not some vast scientific conspiracy. It is not a cover-up or a lie. It is also not about to collapse tomorrow in some Hollywood-style global catastrophe. This is a slow-motion crisis, documented in open scientific journals. While the timeline remains fuzzy, the core implications are massive enough to demand an emergency response. Yet the world has not responded. I get why people turn to conspiracy theories. The frustration is based on a real lack of action. The gulf between our data and government policy is massive, but it is not censorship. The conspiracy theorists are just looking at the wrong culprit. It is just simple policy inertia toward a well-understood problem. Now you and I need to face the most critical question of all. It is the question all our data points to. Is the Atlantic circulation crossing a threshold right now from which it can never recover? Are we watching a massive tipping element fail in real time? Part 12. Is it happening now? Let us bring this all the way home. Every instrument we use points here. The Caesar fingerprints, the Thornalley sediment samples, and the deep sea rapid array. Greenland's gravity data, the Stommel stability equations, and the historical Younger Dryas analogue. The Ditlevson warning signals and Portman's constraints all ask the same thing. Are we hitting the tipping point right now? Have we already pushed past the point of no return? Will the next few decades of monitoring data show this slow weakening finally transitioning into a total collapse? My honest assessment, being as precise as possible because I do not want to mislead you, is that we simply do not know yet. It is not because the science is flawed or the data is hidden. We simply do not know because this system is massive and incredibly complex. On a human timescale, approaching a tipping point looks almost exactly like the same slow weakening we have been seeing for decades. By the time we see the definitive signal that the threshold is crossed, the transition is likely already underway and largely unstoppable. That is the terrifying nature of tipping elements. They do not send a warning flare. They do not announce their arrival. Once the telemetry confirms a tip, any chance of meaningful intervention has basically vanished. Our only window to act, the period where mitigation still matters, is before the threshold has been observably crossed. If you wait for clear proof, it is already too late. You have to move based on probabilities and partial evidence. We have to trust the converging signals from different studies, even if no single data point is a smoking gun. Deep time records show the system can flip. Our current fingerprint shows it is at its weakest state in 1600 years. Direct mooring measurements show a 15% weakening since we started using satellites. The early warning signals are all exhibiting classic tipping point behaviours. Our emergent constraints suggest we have underestimated sensitivity. Plus Greenland's meltwater forcing, the very thing driving this weakening, is accelerating. Alone, none of these are proof. Together, they are a chorus. Experts like Stefan Rahmstorff see a high probability of a total shutdown. Scientist Bubbers notes that these early warning signals are already appearing in our salinity data. The Ditlevsons estimate a collapse by 2057. The IPCC-AR6 is less certain, but still flags it as a risk. Christine Portman argues our models are underestimating sensitivity by nearly double. Look, the scientific chorus is not perfectly unanimous. We debate the timing and the magnitude, but those are just details. The core reality is no longer in question. The direction is settled. I want to tell you my conclusion, as someone who spends every day analysing this data and the surrounding literature. I have tracked this debate for years. You deserve a clear perspective, not just another carefully hedged summary from the lab. This circulation system is in trouble. It is far more serious than official projections suggest, and I think Portman's sensitivity corrections are right. To me, a 50% weakening by 2100 is not the worst-case scenario. It is the most likely one. The regional impacts on Northern Europe and the US East Coast will be far worse than we are planning for. As for a full collapse, that is still the unknown. Based on our trajectory, the data points to a 5 to 30% probability, pending certain thresholds. Given the catastrophic scale of these consequences, I believe this risk level warrants an immediate, planetary-scale emergency response. In my view, the 2057 estimate is overly precise with its date and far too narrow in its confidence range. Yet the broader message holds. Our planetary data confirms the collapse window likely sits within this century, not the next. The next 2 decades are the critical window. If this weakening continues at current rates, our primary risk models stay active. We still have time, but if the slowdown accelerates, that window vanishes. Our sensors, the OSNAP array and Abyssal Argo network, must stay online. If our next-gen satellites detect erratic behaviour in the subpolar gyre, the entire scientific discourse will shift overnight. Accelerating sea levels on the east coast are clear planetary fingerprints. Rising melt rates in Greenland prove that freshwater forcing is compounding. If that North Atlantic cold blob expands, the surface data is undeniable. Every signal asks one question: is the planet flipping now? The Younger Dryas proves this system can flip. Geologic records show it has happened before. Today the system is at its weakest in 1600 years. The orbital level math proves these planetary states can shift, and when they do, the transition is often abrupt and violent. Greenland is bleeding into the same oceanic tipping point we have seen before. The cold blob, the Gulf Stream, every planetary marker is blinking. These changes are happening right now on the very planet we are currently inhabiting and observing together. Whether the threshold hits in 2037 or 2085, the moral weight of our data remains exactly the same. These dates fall within our current lifetimes. The collapse is coming faster than any mainstream climate model has dared to suggest. Every scenario brings global consequences that our current planetary infrastructure is simply not equipped to handle. As scientists, we know even a low probability collapse of this current system is a risk too massive to ignore. Being wrong here is equivalent to a moderate nuclear exchange or a major asteroid impact. The planetary impact would be absolute. We do not manage our space stations or cities by ignoring low probability, high impact disasters. We prepare for the worst case scenario. Yet, because this threat comes from an invisible planetary process with a complex acronym, we treat it like harmless background static. This is not static. The planet's massive heat engine is stalling, and the trajectory has the entire scientific community on high alert. This is happening within our lifetimes. Let's look at the data together. Are we actually flipping the planetary switch right now? We lack absolute certainty, but the converging evidence makes it impossible to dismiss. We are still within the window of action. We are in the pre-threshold window. Right now, we are analysing data fingerprints, not documenting the death of a biosphere. Do we act on these signals before the system dies? This Atlantic conveyor has powered human civilization since its inception. It fueled every empire and harvest. It provided the planetary stability that allowed cities, science, and agriculture to flourish. It sustained everything we know as modern life. A silent, reliable engine working quietly in the background of our biosphere. For millennia, it was an undiscovered mechanism. Now we have mapped it, and we know it is slowing down. Nearly 13,000 years ago, it did not slow down gently, it snapped. The entire climate remained broken for over a millennium. Another snap is no longer a question of theoretical physics. The laws of motion are already in play. Greenland's ice will melt as the thermal energy rises. The North Atlantic will continue to freshen as the freshwater pulse accelerates. The current will slow as the forcing dictates. The remaining variables are the only ones we humans can still influence. We control our carbon output, our planetary cooling efforts, and how fast we deploy our deep ocean monitoring systems. These systems will tell us if the line is crossed. The Atlantic has been broadcasting a warning for 50 years. It speaks through cold blob anomalies and sediment data. It signals through tide gauge records along every eastern coastline. We see it in fossils and the slowing Gulf Stream. We see it in the thinning of the Greenland ice sheet. Every weather satellite in orbit records the declining salinity of the gyre, pixel by pixel, in haunting thermal detail. The data says the engine is failing. It tells us it has failed before with severe results. We still have time. The message is clear. Look up. 13,000 years ago, this very ocean snapped from one stable state into total chaos. A warming continent froze in just 30 years. That deep freeze lasted for over 12 centuries. We are repeating the exact experiment that triggered the last collapse. The question is not if the planet can flip, it is when. Are we flipping it now? Every instrument on our satellites and in the depths shows the system weakening in real time. This era of observation is also our final window of agency. We are the first generation to witness it and change it. Consider this last bit of planetary perspective. You and I need to grasp the sheer scale of the system we are discussing. The man who first calculated this math in 1961 did so using only a slide rule and basic paper. He lacked our modern eyes in orbit, no gravimetry data, no rapid array sensors, none of the high-resolution cores we track today. Instead, he relied on crude hydrographic measurements, fluid dynamics, and a terrifyingly sharp intuition about how planetary waters move. From those fragments, he sketched a model that predicted a silent tipping point within the Atlantic conveyor, using nothing but pure theory. 6 decades later, our orbital telemetry has mapped the cold blob. Modern core samples have confirmed a 1600-year low in circulation. Deep-sea arrays have now detected a 15% weakening in the system. Every signal we capture from space aligns with the math Stommel wrote down in 1961. This is true consensus. Thousands of independent observers and different sensors, all watching the same catastrophic signal emerge across decades. It is not a headline. It is a slow, quiet convergence of terrifying facts. Think of it, math from 1961 ignored for 30 years until a global network of researchers finally began to see the patterns. They spent 60 years building the proof that the theory was right all along. The AMOC collapse is not a sudden surprise. It is a 60-year-old prediction finally manifesting in our data. You and I are the generation witnessing this planetary gear shift. It is a haunting privilege. Our current planetary awareness, the integrated theory and real-time monitoring, is more advanced than anything humans have ever possessed in our history. We are seeing global shifts our grandparents would have mistaken for science fiction. The thermal signatures, the Greenland melt, the deep currents, we see the math coming alive. This is the inheritance of thousands of scientists, quietly tracking the Earth's vital signs for over 60 years. They have mapped this reality for us, pixel by pixel. Now we have to look. You and I need to face the ocean. Look at the cold anomalies on the map. Watch the rising tides. Compare the frozen Hudson Bay to the warmth of London. Look at the massive freshwater discharge from Greenland, visible on the phone in your pocket via real-time satellite imaging. Observe the tropical rain belts shifting and the evidence buried in the deep sea floor. A chorus of global data is shouting the same warning from every lab on Earth. Just look. When the engine of our climate finally stalls out, will anyone on this planet actually notice before it is too late? The next fingerprint, the next signal from the deep, is likely already moving toward us. Only those watching the telemetry will see it coming. The ocean has been screaming for 50 years. The data is right there. But are the people in charge actually looking at the screens? Can we, the ones watching the satellite feeds and the rising water, can you and I make enough noise before this warning signal becomes a final transmission from the other side of the threshold?